This meeting is being recorded.
Okay, well, we'll be looking at visualizing quaternions. And I will make sure my audio is being shared, though people are free to mute me and watch it on their own pending. So here's a link to the article we're looking at. Article, explorable video series. I don't know what to call this. If anyone isn't familiar, quaternions are a mathematical tool that is very useful for 3D rotation, but I have no clue how to explain them and or if I even understand them because they are complex things. So
Well, that's how we're doing this, right?
yep. So let's see.
Quaternions are a four-dimensional number system,
Can y'all hear it?
meaning each individual quaternion consists of four real number parts, like what you see on the upper left here. And one of the main use cases for quaternions is that they give us a really useful language for describing and for computing orientation and rotations in three-dimensional space. My goal is for you to come away from this full experience understanding how exactly that works. And in the spirit of getting you playing with things from the start, I want you to start messing with these four numbers you see in the upper left. If you're on desktop, you can bring your mouse over them and either scroll while the cursor is hovering over it, or grab it to change it. And if you're on mobile, you can tap to interact. And as you change these numbers, you'll notice a couple of things. First of all, changing them causes the sphere that you're looking at to get reoriented. So this is what we mean when we say a given quaternion corresponds to an orientation in 3D space. And another thing you'll probably notice right away is that as you change one of these numbers, some of the other ones are forced to change as well. This is because the quaternions which describe rotation in 3D space are the unit quaternions, the ones where the sum of the squares of these four numbers equals 1. You might also be wondering about this second quaternion written below. And for the moment, I say don't worry about that one too much. In due time, when we understand why quaternion multiplication describes rotation the way it does, you'll know why this second one has to be there. But for this module, my only goal is for you to build an intuition for which quaternions correspond with which rotations. And depending on how brave you are to poke around and see some of what else is lurking within this applet, you might get to a point where things start looking truly strange. And that's because, in some sense, the image I have initially pulled up here of what seems to be just an innocuous sphere in 3D space is actually part of a much broader context of a four-dimensional hypersphere, which in later modules we're going to come to understand. But for the moment, for the purposes of just building up the intuition on which quaternions give which rotation, you don't need to worry about that. You can just think of this as an ordinary sphere in ordinary 3D space, no added frills or complications. One of the first things you might do to build a little intuition is notice how this sphere changes when you just change the I component to go from 0 up to 1, or if you do the same changing the j component to go from 0 up to 1, and likewise for the k. And if you want, please, by all means, pause my voice and just keep playing with that if you feel like there's good intuition to be built.
I think I linked it in the chat. It's
well, it seems like there's like some interactive
yes, it is way more interactive than I thought it'd be. I thought it'd be just a couple of videos, but
it's in the video.
It is a interactive video, and it's a very trippy experience because while I can like touch and play with everything, the Grants who that's weird is narrating it, but also adding and modifying things, and I don't not quite know what to make of it.
Interesting.
I recommend just for everyone else to just open it and then pause the video and then just so you can play around with it.
Yeah, that I absolutely agree with that. Don't just let me show you stuff. Do it yourself because I am not you.
I see. Cool.
Like if I make Q to have a value of 1 and then I start modifying things kind of behave like a axis Euler angle kind of thing where things rotate nicely, which I guess is nice. So you have if you start with a Q of 1 and then you can modify individual ijk values to get an individual axis of rotation. So like this J1 is rotating about the y-axis, whereas the K is rotating about the z-axis, whereas the I is rotating about the x-axis, which is like the basic Euler angle stuff that I am aware of.
By the way, we are seeing your like the the main article rather than your interaction.
Oh, is that what's going on?
Wait, no, I'm seeing the interaction.
Oh,
Really?
Pretty sure, yeah.
That's what I'm saying. Yeah.
So you mean Charles screen sharing?
Yeah, I see the like sphere in the middle and all the controls and stuff.
So my Zoom is bugged again.
Oh no. It's always
Okay.
your Zoom.
Yeah.
Oh, I don't know if you noticed, but you can uncheck that little link icon on the left next to the P, and then it makes them no longer inverse.
oh, okay.
Oh wow.
He talked about it later.
Yeah.
Jeez.
Oh,
Yeah, but this if it's no longer inverse, then it's no longer a rotation. It can do some other transformations.
oh, well, this is a cool transformation. It goes as I get bigger and bigger. It like, what is it? It warps around. It goes from a circle, and then it's the circle turns inside out. That's interesting, but
Some wild stuff.
yeah. I'm gonna keep playing the video now.
But a slightly more generalizable way to understand which quaternions give which rotations will involve changing the representation here to a certain angle axis representation.
Oh,
So in this case, the
Yeah.
real part is written as the cosine of a certain angle. And you can think of the three imaginary dimensions as representing a certain axis in three-dimensional space, just being scaled down by the sine of that angle to make sure that the whole thing is still a unit quaternion. So it's still just four numbers, where the sum of the squares of these numbers is constrained to be 1, but it's written in a different notation.
interesting.
So right now I have that axis set to be fully in the I direction, which you can see with this pink vector coming out of the middle. And what I want you to do is play with this value for the angle. Notice what it does to the sphere, and see if you can predict which angles correspond to which orientations.
So I could change the thing here, but
So the first thing you'll probably
Oh.
notice in doing this is that everything is rotating about the x-axis, which corresponds to the number I. Now, another thing you might have noticed is that there's a certain angle doubling thing that happens here. Notice, when we change this angle from 0 up to 45 degrees, the sphere is actually rotated 90 degrees. And if I push that up to 90 degrees, the sphere has actually rotated 180 degrees. That fact might seem a little bizarre, but it has to do with the idea that there's two quaternion products happening here. One by Q from the left, and one by Q inverse from the right, where in the angle axis representation, you can think of Q inverse just by negating that angle. Just to give a little sneak peek as to why this angle doubling happens, for example, how putting 45 degrees in here gives us a 90-degree rotation. Multiplication by Q corresponds to rotating by 45 degrees, but altering that sphere in a certain way. Multiplying by Q inverse from the right, where with quaternion multiplication, it matters which side you're coming from, involves continuing that rotation, but putting the sphere back in place. Don't worry if that doesn't make sense. I just want to give a little hint about what's going on. So the next thing I want you to do is change this axis by altering the values of either I, J, or K. And as you change one of those values, you'll notice that the other ones change, and the reason for that is to constrain it to always be a unit vector. It has to be the case that the sum of the squares of these three numbers equals 1. So you're playing a sort of continuous whack-a-mole. So go ahead, change that axis in some way, and then notice how the sphere rotates when you then change the angle.
I mean, I've actually seen it described before that a quaternion
What you'll
is like
notice, and maybe this is what you'd expect,
an axis angle, like a vector, and then a rotation around that vector. And I'm like, well, this representation makes that plain and obvious, but the four components Q, I, J, K does not. So that's interesting. No.
Effect is that the values for I, J, and K determine the axis of rotation. As before, you have an angle doubling that goes on, so scrolling from 0 up to 180 degrees rotates the sphere a full 360 degrees. Feel free to stick around here if you think there's more to be done to build some more intuition. Otherwise, to move on, go ahead and exit out of this module.
Yeah. Well, ah, does everyone want to move on to the double cover, the second part?
Yeah.
Yeah.
Cool. Yeah.
So just to give you a little more concrete challenge, I want you to find for me which quaternion corresponds
Oh,
to a 270-degree turn around the z-axis, okay? So 3/4 of a turn around the z-axis, let's say in the counterclockwise direction as you face it from above.
I mean, I wish I could zoom in, but it was the one in the K is now aligned with the z-axis, and so if we rotate, we get a nice rotation. And to find that it was K, I just started fiddling it until the arrow pointed in the direction I wanted. Oh, but if K corresponds to how far up and down the arrow points, so 1 is pointed up and -1 is pointed down. Interesting.
All right, so the way you do this is first set the axis to be fully in the z direction. So the k value is 1, but the I and j values are 0. And as we alter our angle here, bringing it up to 45 degrees gives us a quarter turn. Changing the angle up to 90 degrees gives us a half turn. So it's when you change it all the way up to 135 degrees that we have 3/4 of a turn. So rotating the sphere 270 degrees involves changing this angle to be half that, 135. And if we change out of the angle axis representation, we can see this simply as a quaternion with 4 components. And you'll notice that it has equal parts real and k. But I want you to notice one more thing here. There's 2 ways we could think about orienting the sphere like this. What I just did, we rotated it 3/4 of a turn counterclockwise, right? But you could also just rotate it -90 degrees, which involved changing that angle to -45. And when you do that, and you look at what quaternion's being represented, again, it's equal parts real and k, but it's actually the negative of what we had before. Before, the real part was negative and the k part was positive, but here the real part is positive and the k part is negative. So we have 2 separate quaternions corresponding to the same orientation in 3D space. The phrase you'll sometimes hear referring to this phenomenon is that quaternions are a double cover for rotations in 3D space, which basically means any given orientation corresponds to 2 separate points on the opposite side of a hypersphere in 4 dimensions that we cannot see. And the reason this happens is because of the angle doubling phenomenon, right? I mean, think about it. As we change this angle up to 180 degrees, the orientation it corresponds to rotates 360 degrees, getting back to where it started. However, the quaternion it's representing has rotated 180 degrees around the hypersphere. In this case, it went from being 1 to being -1. So go ahead and keep playing around a bit if you'd like to build that intuition for which quaternions correspond to which rotations. And in the separate sections, I'll explain why this happens in the broader 4-dimensional context of what quaternion multiplication does to a hypersphere.
So it seems there's some 2D visualizations as well. So if you wanted to look at what a one-dimensional, two-dimensional quaternion would be, yeah, a rotation in a one-dimensional context. And of course, there's the imaginary plane. So, okay, what's the 3D one look like? Oh, this is, so it's a two-dimensional plane.
I think it's useful to just go forward because
Yeah.
it is related to the stereographics projection.
Okay. Quaternions are 4 dimensions. Oh, yeah, unit quaternions are all sit a distance 1 from the origin in a 4D space. Stereographic projection. Okay, so to actually understand quaternions, we have to start with 2D planes and projections into them. So just like a map, a 2D map is a projection of the globe. Different projections do different things, but one of them, like this one, has, well, it doesn't have the infiniteness of what it mathematically has, but we'll see what he says about it.
So
Essential
the idea of
angle axis thing, essential math. Yeah, I've seen the axis angle stuff in multiple places talking about quaternions. So
graphic projection is that it gives us a way to map a circle in 2 dimensions onto a line in 1 dimension, where the circle goes onto the entirety of that line, or a sphere in 3 dimensions into the entirety of a 2-dimensional plane, or even a hypersphere that we cannot see and it's invisible to us into the entirety of 3-dimensional space. And to build up an intuition for exactly how that works, it really helps to just start down in 2 dimensions and really understand what's going on here. So we're thinking of the 2D plane in this case as the complex plane, just to be analogous with quaternions later on, and somewhat arbitrarily we're choosing to project from the point at -1. And what I mean by that is you might imagine a bunch of rays of light emanating from that point at -1, and then for any other point on the circle, like in this case the point at coordinates 0.5 plus 0.87 I, if you look at the ray of light from -1 through that point on the circle, it intersects the vertical line at 1 and only 1 point. So what we say is that that point of the circle gets projected onto that point of the vertical line. And what you can see here is that every point of the circle is associated with a unique point on the line, except for -1, which actually has no projection. But because as you approach -1 from either side, the point on the vertical line that it corresponds to tends to rush off towards infinity, we say that this point at -1 is associated with an added point to the line, the point at infinity, which you'll approach if you go in either direction. So to think about a stereographic projection, I think it's helpful to keep in mind just a couple of reference points. So one of the main ones in this case is that the number 1 all the way on the right side of the circle gets projected straight to the center of the line. The purely imaginary units, I and -I, each sort of stay fixed in place, so to speak, which is to say that even when you're looking at the line on the right here, I and negative I are just 1 unit above and below the center. And of course, negative 1 is off at infinity. So those reference points are sort of helpful for getting one's bearings. Now, the other super important thing to keep in mind about stereographic projection is that if you're just looking at this line on the right, and you're meant to understand that that represents the unit circle, you have to remind yourself that the only points you're looking at are a distance 1 from the origin. And this applet has a way of hopefully making that feel kind of visceral. So if you look at the number in the upper left here, it's giving you a complex number, and you can tweak either one of its coordinates if you want. Go ahead and try it. Just kind of put your mouse over there and either grab it to change it or just scroll. Or if you're on mobile, you can tap to change it. And what you'll notice as you do this is as you change one coordinate, the other coordinate is forced to change as well. And it's forced based on the constraint that the sum of the squares of these two coordinates must always be 1. Which is to say, the point they're corresponding to, which we see as this red dot in 2D space, must always be on the unit circle. So I think a really helpful exercise for you right now would be to play around with these two numbers, but focus only on what it does under the stereographic projection, which is the line on the right here. That'll really help to build intuition for how changing coordinates in a higher dimensional space, subject to this constraint that their sum of their squares is always 1, corresponds to your view of it under a stereographic projection. So go ahead and do that. Pause, play around with these numbers, and see if you can build an intuition for what it does to the red dot on the right here. All right, so one.
Ooh.
It's interesting. It's, so you're kind of looking at, some real part and imaginary part. It's like,
Yeah.
it's just on the circle. That's interesting.
And the circle is mapped to a line which extends to infinity.
Yeah.
So as you bring the point closer to -1 on the circle, it goes to infinity. And then as soon as you go past -1, it wraps to the other side. It is a projection where you're drawing a line between them and marking out a point where it crosses a different line. In our case, the vertical negative, or the vertical axis, which corresponds to the imaginary plane. Axis imaginary.
One thing you might notice in doing that is that if the coordinates start off with a positive real part, meaning you're on the right side of the circle, which places you sort of between I and negative I under the projection, then if you're just changing the imaginary component, I and negative I, that just moves your red dot within that interval on the line. But if you change the real component, that sort of controls how far away from the center you are, which kind of makes sense, because as you're changing the real component, it's ranging from 1 to -1, and under the stereographic projection, 1 is at the center of the line, and -1 is off at the point at infinity. So maybe it kind of makes sense that the real part tells you how far away from the center you are, where the more negative the real part, the farther away from the center. Okay, so with that said, let's see how all of this looks in 3 dimensions.
Which is the next thing.
So the idea of stereographic projection is that it gives us a way to map a
little bit of chink.
So here we have a sphere, and the sphere is getting stereographically projected onto a plane. And what I mean by that is you sort of imagine shining a point from the very bottom of that sphere, the South Pole, and for any given point on the sphere, you look at where the line through that point intersects the plane, and that gives you an association between points on the sphere and points on the plane. And in the upper right, you can kind of see a copy of that plane. And as that sphere rotates, you can see what that does to the stereographic projection of it. Okay, so you might be wondering about the coordinate system and the controls that I have in the upper left here. So to make things analogous with quaternions, the way I want you thinking about this is that the z-axis, perpendicular to the plane, is the real number line, with the number 1 sitting a unit above the plane, and the number -1 sitting 1 unit below the plane. And then the plane itself is spanned by the I and the j axes, where the y-axis is our normal imaginary numbers, and then the j-axis is sort of like a new dimension of imaginary numbers. Now this coordinate system with one real dimension and two imaginary dimensions is not a number system the way that the complex numbers are or that the quaternions are, and I'll say a little bit more about that in a moment. But again, it's very helpful for thinking about quaternions to think in terms of this coordinate system. So the number that you see on the upper left here determines where that pink dot that starts off at the North Pole at the number 1 ends up. And as you change those numbers, the sphere is going to rotate in some way that moves the pink dot, North Pole, to the coordinates that you've specified. And again, one of the really important points here is that the stereographic projection is only being applied to the points a distance 1 away from the origin, where the sum of the squares of these components is equal to 1. So to make that constraint feel very visceral, as you try to change one of these coordinates, the other two are forced to change so as to maintain that property. And I'll mention in a moment why we put this little rotation control there as well. So the first thing I want you to do is limit your attention just to the pink dot on the sphere, and also where that pink dot goes in this 2D view on the upper right, and see if you can build an intuition for where that goes as you change the coordinates. So for example, as I change I to be 1, that pink dot moved to the spot 1 unit on the right. As I change j to be 1, that pink dot moved to be 1 unit above the center. And of course, as you're doing this, the whole sphere is rotating and you're seeing its various octants, but just limit your attention for the moment to that pink dot and play around for a little bit. So one thing you might notice in doing this is that the imaginary coordinates, I and j, seem to control the direction of that pink dot. If I is 1, that pink dot is pointed to the right. If there's a little bit more of a j component, then it's pointed right and up a little bit. And then that real part, as you change it, controls how far away that is from the center. And again, that kind of makes sense. If the number 1 is at the North Pole, and that gets projected straight to the center of the plane, -1 is at the South Pole, getting projected off to the point at infinity, then the closer you are to 1, the closer you are to the center of the plane, and the closer you are to -1, the farther away you are from the center of the plane. Again, this is something you'll see as you play around in the 4-dimensional view. Another thing I want you to notice here is what happens to the circles on the sphere as you rotate it under this stereographic projection. So for example, maybe just focus on that equator, the yellow circle. As you rotate the sphere in some way, that equator might get tilted out of place. And as it does, what you see under the stereographic projection is that it seems to grow and warp. But of course, on the sphere itself, it's not changing shape. It's just getting reoriented. All of that warping and all of that growth is just an artifact of the projection. And you'll see things very analogous to that when we're in the 4-dimensional view. All right, so what about this other control here, this rotation? The reason I wanted to put that there is to emphasize a certain point about rotations of the sphere. So this top control is just telling us where the North Pole goes. And really there's only 2 degrees of freedom of that. You might think of it as the latitude and the longitude for where that pink dot ends up. Or maybe you think of it as we have 3 numbers, but they're subject to 1 constraint, so that gives us 2 degrees of freedom. But that fact alone, where the North Pole goes, does not uniquely determine a reorientation of the sphere. You have this separate degree of freedom based on how the equator rotates. So the point here is that you need 3 degrees of freedom in order to describe a reorientation of the sphere. And that's sort of different from how it is with the complex numbers. You have 1 degree of freedom to describe where you are on the circle, but you also only need 1 degree of freedom to describe a unique rotation of that circle. And that's sort of why complex numbers on the unit circle give us a way to compute and describe rotation. A given point on that circle can be associated with a rotation of that circle. But you can't do the same thing in 3 dimensions. You can't uniquely associate a point on the sphere with a rotation of that sphere, because you're still missing a degree of freedom. And that's part of the reason why you need to go up to a 4-dimensional number system to describe reorientations of a 3-dimensional sphere. Because in much the same way that it requires 2 degrees of freedom to tell you where you are on a sphere in 3 dimensions, it'll take 3 degrees of freedom to describe where you are on a hypersphere. And those 3 degrees of freedom really nicely correspond to the 3 degrees of freedom for how you rotate a sphere in 3-dimensional space. All right, so let's jump up to 4 dimensions. So here we have a sphere, and the sphere is getting stereographically projected onto a plane. And what
Oh, I didn't want to full screen that. Nope. Wo-
So in this section of the applet, the entirety of three-dimensional space that you see, and the various objects that you might see within it, are a projection from a hypersphere in 4 dimensions that we can't see. So whereas in 2 dimensions we had the crutch of actually knowing what
I'm going to start this again because it was lagging for me.
this section of the applet, the entirety of three-dimensional space that you see, and the various objects that you might see within it, are a projection from a hypersphere in 4 dimensions that we can't see. So whereas in 2 dimensions we had the crutch of actually knowing what 2-dimensional space was, then on the right here there's the image just of the projection, and in 3 dimensions we had the crutch of understanding a 3-dimensional sphere, and then in the upper right here there was the view just of the projection. We don't have such a crutch for a hypersphere, since that's beyond our perception, or beyond my perception at least. I can't speak for you. Now the controls in the upper left here are set up specifically to be able to play with quaternion multiplication, which we'll get to in just a moment, but right now all we care about are individual points. Nevertheless, it might be a little helpful if I talk through what we have up here. So there's one quaternion, Q1, which is a point in 4-dimensional space, and similar to what you saw before, if you try to change its coordinates, it's always constrained to have a unit length, meaning the sum of the squares of these numbers is 1. And then we have some other point, P, where you can select various options for which point you want to see, or maybe collections of points, like a whole circle along the hypersphere, or a whole sphere of points on that hypersphere. And the letter P is just meant to denote one of those points. And then Q2, some other quaternion. And what you're looking at is the output of the product Q1 times P times Q2. And again, later on we'll talk through what quaternion multiplication does and how to think about it. And you'll see why setting things up this way with Q1 and Q2 sandwiching the point P is useful for understanding how quaternions relate to 3D rotation. But right now, the only thing we need to do is focus on a single point, a single quaternion, to get a sense for what this stereographic projection is doing. So Q1 will be that quaternion that we want to look at, and the only point that I'm going to show for P in the middle here is 1, and then Q2 we're going to leave that fixed at 1. So when you look at the output of this function, Q1 times P times Q2, it's Q1, some 4-dimensional point, times 1 times 1, so it stays the same. Take a moment to do this. Change the various 4 coordinates, the real part, the I part, the J part, and the K part, and see what that does to our point and where it ends up in 3-dimensional space.
I'm going to reload the page because I was getting massive lag. See if that helps.
So in this section of the applet,
Oh,
the entirety of 3-dimensional space that you see, and the various objects, this section of the applet
I think my computer's just overloaded. I don't quite know what's going on.
so it stays the same. Take a moment to do this. Change the various 4 coordinates, the real part, the I part, the J part, and the K part, and see what that does to our point and where it ends up in 3-dimensional space. What you might notice in doing this is that the I, J, and K part seems to control the direction for where this point is away from the origin, and then the real part controls how far away it is. When that real part is close to 1, you're really close to the origin. And when that real part is close to -1, you're close to the point at infinity, which is to say you're far away from the origin. And this should feel very analogous to what was happening in 3 dimensions, where maybe we view this sphere from head on to notice how the imaginary parts give us a direction away from the origin, and then the real part tells us if we're close to the north pole of that sphere, which gets projected into the center, or if we're close to the south pole, which gets projected to the point at infinity. And as you change this value, Q1, see if you can kind of predict a little bit how that change is going to influence where the point F1 is.
Hmm. So it seems that quaternion multiplication is just a regular multiplication, like of terms, but you have a couple of identities that you can use to simplify things. So that's nice.
Well, and they're all cross products, right? In a right-handed coordinate system. So like I is X, J is Y, and then so I cross J is K.
Oh, that's what you mean. Yeah, okay. Yeah, yeah. Um,
So by now, hopefully you've built up at least somewhat of an intuition for what I mean when I say the entirety of 3D space you're looking at right now is a stereographic projection of a four-dimensional hypersphere. The reason for going through all the effort to view the 4D sphere in this strange way is that it makes it possible to look at something quaternions are doing up in 4 dimensions down here in 3. Namely, the quaternion multiplication looks like two rotations that are, in a sense, perpendicular to and in sync with each other. To understand what I mean by that, let me first show you how quaternion multiplication is an extension of complex multiplication.
did we skip part of the last video? I don't think so. There's a bit of text that separates the stereographic projection idea from the multiplying quaternions. So I can go back if you want, but I'm just going to plow ahead then.
So
Okay.
in the complex numbers, just on a 2D plane, if we multiply by I, the effect that this has on any other number is to rotate it 90 degrees counterclockwise about the origin. And more generally, any other complex number on this unit circle corresponds to a certain rotation. And the way you can think about that rotation is by imagining grabbing the point at 1 on the right here and moving everything in the only rigid motion possible that puts 1 on that special number. One kind of nice way to represent things here is if I switch the notation for our unit complex number to be written with an angle, where the real part is the cosine of some angle, that gives you the x distance, and the imaginary part is the sine of that angle, that gives you the y distance. So notice as you change this angle, the red dot it corresponds to on the circle is rotating. It ends up that angle away from the horizontal axis. And in fact, it wouldn't be a bad idea to right now play around a little bit with this angle and think about what this looks like on the stereographic projection of the circle, which is just a line as you see on the right here. Because if you understand what rotation looks like there, then it won't seem so crazy when I go up to our four-dimensional view and I say that multiplication by I, where our view is just restricted to a single circle up on that hypersphere we can't see, looks something like this, and how that's actually a 90-degree rotation. In fact, I can switch our view here also to be in a notation that shows things in terms of angles. So here, as you change that angle, you'll see this strange morphing motion along a line in the x direction, but we can understand that that's actually the stereographic projection of a circle up on the hypersphere. And more concretely, here's what I mean by multiplication acts this way. So what we have in our viewer here are 4 different points: 1, I, -1, which at the moment is at infinity, and -I. And the function being applied to it is to take q1, whatever we've set in that upper left, times that point, and then q2 at the moment is just the number 1, but we'll be changing that in a few minutes. So for example, if you want to see what I times 1 is, change q1 to be I, And notice what f of 1 is. It is now in the point where I used to be. So I times 1 is I, which should make sense. Similarly, if you want to see what I times I is, well, notice what happens to f of I here. It slides off to the point at infinity, which is -1. So this is our applet showing us that I times I is -1. Likewise, if you want to pause here, you can take a moment to think about what I times various other values gives us. Now, one sort of hack that we can do here is if I change Q2 in some completely random way, where you don't need to worry too much about what exactly this means, the effect is basically to change our view of the hypersphere so that when we're displaying this circle through 1 and I and -1 and -I, we actually see it as a circle rather than getting projected onto a line. And when we do that, and we multiply by I from the left, maybe it seems a little more reasonable how this is supposed to represent a 90-degree rotation. Or if we shift the notation a bit, how it can represent rotation by any other angle. Now let me set things back to where they were, and let me ask you, what does multiplication by I do to the other quaternions up on the hypersphere, like J and K? Well, take a moment right now to play around. If we display f of j and we display f of k, what happens as you change q1 to be I? Well, what you'll notice is that they rotate 90 degrees.
Don't know. Just wanting to play with it, and he did stuff. Um, huh.
Okay, so the axis there, then you're okay. So that's like the number line that was being projected on in the lower dimensions.
Yeah.
Right, and as you play with those angles, those two yellow spheres are constrained to that axis then.
Yeah. And then we have the f of I over there doing a circle around the axis, whereas f of k is going through the infinite projection, or projection to infinity. Interesting that f of -1 and f of or negative I and I are. Well, that's j. F of j. Is negative j just not there? Okay. Yeah. Interesting.
Well, what you'll notice is that they rotate 90 degrees about the I-axis. And in fact, if we also pull up negative j and negative k, and in fact the whole circle passing through j and k, that circle rotates 90 degrees about the x-axis. And one way I like to think about which way it rotates is to take my right hand and point my thumb from the origin, where f of 1 gets projected, to I, and then see which way my fingers curl. The direction they're curling tells me which way that perpendicular circle through j and k gets rotated. And again, if we want, we can do a bit of a hack to see this from a different perspective, effectively projecting from another point on the hypersphere. When we do it like this,
Whoa.
we see both circles as actual circles, and as I'm multiplying by I from the left, maybe it makes a little sense how you could describe this as two rotations perpendicular to and in sync with each other. So setting things back to where they were, one property of quaternion multiplication is that order matters. So multiplying by I from the left actually gives a different effect from multiplying from I on the right. So go ahead and try this. Change the value of Q2 from 1 to I, and see if you can tell how that's different from changing the value for Q1 from 1 to I. What you might notice is that almost everything is the same. It's still two rotations perpendicular to and in sync with each other.
Direction.
And in fact, the effect on the circle passing through 1 and I is completely the same. 1 moves to I moves to -1, and so on. The only difference is that the JK circle rotates the other way. You might think of it as obeying a certain left-hand rule now, where you point the thumb of your left hand from 1 to I, and the direction your fingers curl tells you which way that JK circle rotates as it's being multiplied by I from the right. Filling out this picture a little bit more, we could bring in the entire sphere up on that hypersphere that we can't see, passing through I, J, and K, which is something analogous to the equator of a sphere in 2 dimensions that was just in the plane spanned by I and J. And you can notice what happens to that sphere as all of its points get multiplied from the left by I. Now, if this bubbling out feels a little bit weird, consider what happens to the projection of the equator of a sphere in 2 dimensions as you rotate the sphere. As that equator gets tilted out of place, notice that in the stereographic projection in the upper right, that yellow circle looks like it's getting bubbled out, until, for a 90-degree rotation, it actually ends up looking like a line, which is sort of like a circle with infinite radius. Up on the hypersphere, that sphere equator is getting tilted out of place, and after a 90-degree rotation, corresponding to multiplication by I, it's actually in just the right position so that it's projected as a plane. And the reason for that is that one of the points of the sphere is I, right? That's what you see as f of I under the projection here. But as we multiply I times I, you get -1. -1 is at the point at infinity, so the sphere has to pass through the point at infinity, meaning it's a plane. So go ahead and play around with that, see if it feels at least halfway reasonable, multiplying all of the points on the sphere by I from the left, and also see what it looks like to multiply by I from the right. All right, so after looking at all of that, let's think about multiplication by a few other quaternions. Let's say we multiply by J from the left. In this case, the most convenient subsets of that sphere to start looking at include the circle passing through 1 and J, since that just gets rotated, which under our projection looks like this strange morphing, and then to look at the circle perpendicular to that one, passing through I and K. So take a moment to play with that. Multiply just by J from the left, and if you want, just by J from the right, and see if you can build the intuition for what that looks like.
Whoa. Oh, okay. I think it was going into the I, it was changing I instead of Q and making things wacky. Yeah, see. Whee! It's trippy.
This is making me appreciate GLM that much more.
Yeah. Goodness. Ugh.
Again, maybe you can bring in the entire sphere passing through I, J, and K, and notice what the product does to that sphere as viewed under our projection. And finally, for the sake of completeness, maybe you also want to think about multiplying just by K from either side, where in that case, the most convenient circles to look at are the one passing through 1 and K, and the one perpendicular to that, passing through I and J. Now to think about multiplication from any other quaternion that's not one of our units, I, J, or K, from the left or the right, we might switch our notation to this angle and axis, and change this IJK part here, which you can see with this pink vector stemming from the origin. And then notice, if we pull up our IJK sphere, as we shift the angle here from 0 upwards, basically decreasing the real part, but increasing the imaginary part, again, at 90 degrees, that sphere gets perfectly flattened to a plane, specifically a plane perpendicular to that pink vector. And if you'll notice, as you're doing this, maybe if you're facing that vector from head on, the sphere is also rotating perpendicular to that vector. So there's no two ways about it. Quaternion multiplication is weird to think about because it's a 4-dimensional thing Our brains can really only see 3 dimensions. But I do think if you play around a little bit more here, you can get a substantive intuition for quaternion multiplication. And if you need, don't be shy about making things really simple. Isolate it down where you're just looking at one point, maybe I, and you're asking yourself, what does it mean to multiply this by, say, j from the left? And notice what that does to I. Maybe ask, what does it mean to multiply it by k from the left? And you notice what that does. And just keep doing this with several different points and see if you can predict before you change the value where it's going to end up. Where the way you can make that prediction is by asking, which 2 circles should I think about as rotating perpendicular to and in sync with each other?
Oh, ugh.
So by this point, I'm assuming you understand what I mean in saying that quaternion multiplication in 4 dimensions looks like 2 rotations perpendicular to and in sync with each other. And now it's finally time to understand why the function we're looking at is q1 times p times q2, this sort of quaternion sandwich around a point. For our starting example, let's focus in the j direction, along the y-axis. Think about what it means to multiply by j from the left and then the inverse of j from the right. So when I multiply by j from the left, both of those circles rotate, right? And the ik circle rotates 90 degrees. But now if I multiply by negative j from the right, the effect on the circle through 1 and j is completely canceled out, right? 1 moves back to where it started, j moves back to where it started. But the difference is that the circle through k and I continues rotating just as it had been before. So to see this with slightly different notation, let's look at that same process but with angle axis, right? So in this case, our axis is going to be purely in the j direction. And let's say I rotate 90 degrees in the j direction, right? So all circles have rotated 90. Then when I rotate I need to make this the same axis. Okay. So then when I rotate negative 90 degrees from the right side, that ik circle just keeps rotating. And in fact, let's view that whole thing, but bringing in the ijk sphere. The circle through I and k is part of that sphere, so that tells us part of what's happening to it. And then we also know that j, and let me pull up negative j, are the, kind of the poles of that sphere on the axis perpendicular to that circle. So where j and negative j go, along with where k and I go, will fully determine where this sphere goes, at least under the constraint that it's all rigid motion up in the 4 dimensions that we can't see. So as I rotate this 90 degrees, that sphere gets to a point where it's actually projected just as a plane. And then as I rotate negative 90 degrees here, it comes back to where it was, but it's reoriented. Okay? Then we can do this with smaller angles too. Let's say instead I rotated just by 45 degrees. So we'll go 45 degrees here. Okay, and we see that the ik circle rotated 45 degrees. And then I do the negative. And since it's from the other side, that ik circle keeps on rotating, but the sphere is back in place. And the rule is basically the same for any other unit quaternion. It doesn't have to be j. If we did the entire same thing for I might change which circles are easier to look at here, instead looking at the circle through 1 and I, and the circle perpendicular to that, which is j and k. As I multiply from the left, it sort of bubbles that sphere out, and then as I multiply by the inverse from the right, the sphere gets back into position, but it's reoriented. It's been rotated. So with that gives basically the intuition for why a certain quaternion sandwich like this gives us rotation in 3 dimensions. What it's actually doing is a much richer, much fuller motion up in 4 dimensions. We're just being very clever about how if you construct a certain multiplication from the left, and then a certain multiplication from the right, the overall effect just on the ijk sphere, the equivalent of the equator of the hypersphere we can't see, is to reorient it in place. And in the applet, if you click this little link here, what it'll do is automatically make it such that the quaternion on the right is the inverse of the one on the left. So as you tweak the angle and the axis, you don't have to worry about hand constructing that right one to be the inverse. All right, so that's the end of the lesson that I had planned, but don't let this be the end of your actual interaction here. There's a lot that you can do if you add various different elements on here, and I want you to ask yourself questions and see if you can answer those questions just by playing around and maybe popping down to some of the lower dimensions to help build intuition. For example, if you want to understand the angle axis representation here, usually when you see a cosine and a sine, that means you're along some kind of circle. Well, what circle are you along? See what that looks like in 3 dimensions if we represent a point of that sphere, this little pink dot, with a certain angle and axis, and tell me, what circle are you on, and how does that look under the stereographic projection? Likewise, ask yourself different questions, play around with different elements, and I think, very seriously, you could productively spend hours here, maybe even pulling out a pencil and paper to kind of work out some of these products by hand, and seeing how it all fits together.
And some of this by hand and kind of, I feel like working out some of the actual like multiplications would be helpful.
Yeah.
Yeah, I still don't find it super intuitive to wrap my head around the like projection stuff, but it does make sense that you like do half of your rotation, but then that also messes up the rest of your space, so you have to kind of do an extra thing to restore it.
Yeah, visualizing the circle, kind of the sphere, getting warped out into the plane. That visual actually kind of started to make sense, where it's like you had that ring, and the ring stayed fixed, but the center of that sphere shifted out to the right. And so in order for that sphere to line up with the ring, it had to grow, right? And as that center kind of goes further away from the ring, it has to unwrap to a plane.
Yeah, right. that was like, if I do, if I start doing this gets put out here, but you're only halfway done with your rotation, so you have to do the inverse one of here to bring it back.
Yeah, and can you turn the IJK sphere on?
Sure.
Right. So you see how, like, as that point gets pulled off to infinity, right? Or as or maybe if we inverse that, if we pull it back towards the center there, right? So that ring is always perfectly on the perimeter of the sphere there.
I think any any sphere can be determined by 3 points, right? I guess that's the idea.
Yes. Yeah.
And so yeah.
Yeah.
So F of I, J, and K are determining where the sphere is. Yeah.
Mm-hmm. Yeah. No, the visual actually helped there.
Yeah. This was the visual I really liked. The line in the sphere going, the projection of a circle, which looks like a line going to infinity, and the other circle that is, yeah. And then you can do this, and you'll have your here where it's like, oh no, not like that. No, never mind. This is a very useful tool.
Yeah, I think I need to watch it about 5 more times. And
well, I think it would be good for people to, in conjunction of watching this, read a more definition-based description of quaternions, because this is decidedly, you've heard of quaternions before. Let me try to make it more clear to you. This doesn't really tell you if you haven't seen Quaternions before, this is not a good place to start with them, in my opinion.
Mhm.
So I hope no one here is super unfamiliar with them and has just been lost the entire time. Ugh.
It'd be interesting to understand how the like interpolation works too between two
I wonder.
quaternions.
Yeah, chaining these together, yeah. Like to multiply multiple of them together, I guess.
Well, I mean, multiplying them together makes sense, right? Because it's just like complex numbers, right? You're just multiplying them and doing the math.
So by this
But
point,
then
I'm
you can
assuming
also
you
interpolate between two quaternions and get a smooth, or like
Right.
it's a rotation that's on the circle that connects the two or something.
Yeah, I mean, let's look at the sphere and lock it. Like, I wonder if there is some intuition to be had about, because a sphere is not a Euclidean space. If you're on the surface of a sphere, you can only move in two directions. However, because it wraps around, you're not in a space where you can go infinitely far away, or you can go infinitely far in one direction and end at the same point again, which you can't do in, I guess, Euclidean space. So having to be in 4D space may kind of make sense from that perspective, but I think I'm just waxing mathematical more than anything. Okay, here's the book that Leslie likes. Not there. $70. You need a Quaternions for Computer Graphics textbook. If I ask nicely, I think I might be able to find a PDF of it. Though, I guess I'd have to ask nicely. Yeah. So well, there's some, yeah. Apparently nobody has a PDF of it, so. Did that? Okay, okay, never mind. I do not have a PDF of it. That was odd. How does everyone feel about Quaternions?
I felt like that was a interesting visual demonstration. And I think the next thing would be seeing like code and like how it's useful in practice.
Yeah. Because the big thing Quaternions do is efficient concatenation of multiple rotations that doesn't suffer from gimbal lock or loss of freedom of motion.
Also, just interpolation. It's really hard to interpolate to like
Yeah.
rotation matrix nicely.
Yeah. I'm just not going to look at a link that doesn't have. Oh. Yeah, the slurp is the big thing that I understand Quaternions give you. That if you have, say, an animation system and you want to go from hand pointing up to like hand pointing forward smoothly, and with equal distance covered in every time step, the slurp will give that to you, whereas a lerp between the point up and point forward would be would have, it wouldn't be a linear interpolation, it would be discontinuous. How do I put it? It doesn't interpolate nicely.
I
That's
saw when I was reading in the game engine architecture book that slurp actually doesn't give, or I guess regular lerp is not that inaccurate compared to slurp. And so you can actually use it as a decent approximation. Like if you just use a lerp and then normalize, the error will only be obvious if the rotation is, or the radius of the rotation is large.
I guess for small rotations, it's probably even more
Fine.
accurate, right? So
I mean,
Yeah.
the classic physics 1 problem of the equation representing the motion of a pendulum in a clock is a case where we do not actually have you don't use the complex real formula, that the real formula to describe it, because it's complicated, but you can use a very simple, like sine wave kind of thing, and it's close enough for degrees less than 15 or so.
and you can probably do like go halfway between with slurp and then like lerp, like you could like divide or subdivide the rotation and then use lerp between the subdivisions.
That's getting off topic. My point with the lerp versus slurp, the animation actually speeds up and slows down things, but my point was more that as you lerp from A to B, when you're doing a rotation, you're speeding up towards the middle and then slowing down towards A, relative to if you had done a very linear motion over time. Whereas a slurp, you're going to get a perfectly smooth motion across it at the cost of being more computationally expensive.
That's a good point.
I wonder if you could also transform, like if you're going from 0 to 1, if you could use like some kind of smooth step kind of thingy where you're actually not, like using some polynomial that lets it sort of changes the speed of the interpolant. Yeah.
Yeah, it's using a polynomial instead of the actual like formula.
I was watching a video about approximating the curvature of the Earth from like a perspective of a person on the Earth, and they gave a very basic equation that was like x squared divided by 8, which if you used inches and miles, it would actually almost perfectly approximate it out to a couple of hundred miles, which was very surprising. But it kind of reminds me of that, where you use a very simple formula or a very simple equation like polynomial to approximate something much more convoluted, like a cosine. Not that cosines are convoluted, but that they're transcendental and don't make for quick calculation.
Well, I mean, if you actually calculate a cosine or sine on your processor, it's using a polynomial. Anyway.
Is it?
Yeah, because it only has to be accurate to whatever 32 bits or 64 bits or whatever.
I feel like I should have known that, but for whatever reason, in my head, transcendental lookup tables was also a thing.
Yeah,
that people
well, it
did.
just follows the like Taylor series. Like you do Taylor series and take the first n terms or whatever.
Some microcontrollers do like an interpolated lookup table kind of thing.
Okay, so understanding slurp and then not using this. This seems like an article on what
By Jonathan
slurp.
Blow.
Yeah. Okay. Work minimal path is the shortest way from one rotation to another. And the slurp function walks that path. Despite quaternions being very important, few programmers understand how they work. You can say that again.
Yeah.
Yeah, slurp always generates great circles of the hypersphere, and great circles are always coplanar. Yeah, that's something I was understood about slurp is it's like an arc length on the rotation sphere. Zen-like detachment from the idea of coordinates.
I think probably I should stop recording since we are kind of.
We've diverged.
Yeah, and I will cut like this part about slurp off.
Yeah.